Hello everyone, welcome to this video looking at integration by partial fractions. So in this video, I'd like to give the motivation of why we need this method, why it's useful, and do one or two basic examples. And then after that, we'll delve more into the details in later videos. So let's get started. And integration by partial fractions is all about how to integrate rational functions. So rational functions are just things that look like p over q, where p and q are polynomials. So they're just a particular type of function where it's one polynomial divided by another polynomial. So for instance, here are some rational functions. If we were to look at x plus 5 over x squared plus x minus 2, okay, it's a polynomial divided by another polynomial. It's a function, and so it has a particular name that's a rational function. Similarly with x cubed plus x over x minus 1, it's a polynomial divided by another polynomial, so it's a rational function. And x over x times x plus 1 times 2x plus 1, doesn't matter if it's factorized or not, it's a polynomial divided by another polynomial, so it's a rational function. So as you can imagine, there are lots and lots of different rational functions. So as you know, the top could be a polynomial of any degree, the bottom could be a polynomial of any degree. So there are quite a lot of things that we might want to try to integrate. So we're really going to need to have some systematic method to try and break things down. So our question we're going to address in this section is, how can we integrate rational functions rather than just making it up as we go along? And the answer is going to be to first, given a rational function, first rewrite it in partial fractions form. So, sometimes, as we saw with, I guess, with trig functions, that if you rewrite something in a different form, sometimes even though you're just doing an algebraic step to write the same thing in a different way, sometimes that step can make it easier to integrate. So it's going to be the same thing with rational functions. So partial fractions form has a very specific meaning that we'll see in a little bit what we mean by partial fractions form. Okay, but before we do that, let's see how it works in just an example, kind of as a motivation. So let's suppose we want to find the integral of x plus 5 divided by x squared plus x minus 2. And it's not an easy integral. For example, u equals x squared plus x minus 2 would not work because the top is not the derivative of the bottom, so the substitution wouldn't work out nicely. So we need to do something else. And here is a magic trick that's going to become clear a little bit later why this works. So let's suppose we instead start with 2 divided by x minus 1 minus 1 divided by x plus 2. So let me pull this out of my hat. And then let's form a common denominator and see what it's equal to. So if we have 2 over x minus 1 minus 1 over x plus 2, common denominator is going to be x minus 1 times x plus 2. If we want to make that the common denominator, that means we have to multiply the top and bottom of the first term by x plus 2. And we have to multiply the top and bottom of the second term by x minus 1. So we are going to get 2x plus 2 minus x minus 1 over x minus 1 times x plus 2. Okay, and then if we multiply out the top, we have 2x minus x is going to give us x, and we have 4 minus minus 1 is going to give us 5. So we get x plus 5 divided by x squared plus x minus 2. Okay, and surprise, surprise, or maybe not a big surprise, that's the thing we started with, right? That was why I chose this particular expression. So this particular expression, even though 2 over x minus 1 minus 1 over x plus 2, even though it looks very different to the thing we started with, which was x plus 5 over x squared plus x minus 2, it looks quite different, but they're equal if we find a common denominator. And as for how we find this, that's going to be the whole point of partial fractions. So it's not obvious at all that we had to start with 2 over x minus 1 minus 1 over x plus 2. I don't claim that's obvious, but we'll see later how to do this. So for now, just take it for granted that we managed to find this decomposition. So this is going to be our partial fractions decomposition, whatever that is. And then this becomes way easier to integrate. So rather than starting with the original integral we had, we can instead, because they're equal, we can instead integrate 2 over x minus 1 minus 1 over x plus 2. And then on each of these terms, a simple u substitution would work, right? So on the first one, 2 over x minus 1, you could do u equals x minus 1. The answer will be 2 natural logarithm of absolute value x minus 1. And then on the second one, you could do u equals x plus 2, for instance. The answer will be minus natural logarithm of absolute value x plus 2. Okay, and then it's an indefinite integral, so we have the constant c as usual. So we went from a rather complicated integral of a rational function to a way simpler integral that we could actually do just by this algebraic step of writing in a different form. So the whole point of integration by partial fractions is going to be that we need an algorithm, or in other words, a sequence of steps for how to write our rational function in easier form so that we can actually do the integral. So there are going to be 3 steps. So let's look at step 1 and step 2, and then the outline of step 3. And then step 3 is going to be divided into a bunch of cases that we'll look at in the subsequent videos. So what do we have to do in case 1? So as we said, how do we find the right decomposition? We need partial fractions form. So let's talk about step 1. What do we have to do first? So before we talk about that, we need to remember something called the degree. So let's remember that the degree of a polynomial is the highest power of x. For instance, the degree of x squared plus 1 would be 2. The degree of x to the 50 plus 7x cubed minus 9 would be 50. It's just the highest power of x. For instance, here the degree would be 5. The only one that's not so obvious is if we think about what is the degree of a constant. Say I had the constant 5. It's a polynomial. That would be x to the 0. So the degree of a constant is just 0. So that's the only kind of confusing one. And next, a rational function. So remember, rational functions will look like one polynomial divided by another polynomial. So it's p divided by q, where p and q are polynomials. A rational function is proper if the degree of the top is less than the degree of the bottom. And it's improper if the degree of the top is bigger or equal to the degree of the bottom. So somehow we want to deal with proper rational functions, which is when the degree of the top is less than the degree of the bottom. So for instance, x plus 5 over x squared plus x minus 2, the degree of the top is 1 because the highest power is x to the 1. The degree of the bottom is 2 because we have x squared. So the degree of the top is less than the degree of the bottom. This is proper. Okay, but if we look at x cubed plus x over x minus 1, the degree of the top is 3. The degree of the bottom is 1. 3 is bigger than 1. Okay, bad news, that's not proper, or in other words, it's improper. Okay, so step 1 is we have to look at whether the partial fraction we're trying to integrate is proper. And if it's not proper, we have to make it proper by using algebraic long division. So I'm not going to go through how to do algebraic long division because I think it's a bit of a diversion, but we'll do some examples on how that works in class, or you can look it up. Hopefully you saw it already somewhere, maybe in your pre-calculus studies. There are not too many questions where this comes up, but I think it's worth knowing anyway. But for now, I'm just going to take it for granted how to do that, and then we'll do some more examples. So step 1, we look at our partial fraction, our rational function. We look at our rational function, we look at the degree of the top, the degree of the bottom. If it's not proper, we have to use long division to make it proper. Okay, so sometimes that will be enough by itself. So let's suppose we look at the integral of x cubed plus x divided by x minus 1. The degree of the top is 3, the degree of the bottom is 1, so it's improper. So we have to do algebraic long division. And if you run through the steps, you'll see that this can be equivalently written as x squared plus x plus 2. And then there is a remainder of 2, so we have plus 2 over x minus 1. So then this becomes way easier to integrate. So we can integrate x squared plus x plus 2. We can integrate 2 over x minus 1. Now it's a much easier integral that we can actually do. So instead of integrating with the thing we started with, we integrate the equivalent formula. Okay, then we use the power rule in each term. And then finally, 2 over x minus 1, we could do a u sub u equals x minus 1, for instance. It will be 2ln absolute value x minus 1. Okay, so do go back and look at algebraic long division, how to do it. If you've forgotten, we'll do some examples too. But step 1 of partial fractions decomposition is look at your rational function, check it's proper. If not, you want to make it proper by using long division. Notice here that after we had long division, we had polynomial plus something new that is proper. Okay, so that's step 1, but usually it's not enough. For instance, if we look at x plus 5 over x squared plus x minus 2, it's a rational function, it's proper, but it's still not an easy integral. So just making it proper is not enough by itself. This example was kind of nice, but most examples are not like that. So we need a step 2. So what do we go on and do in step 2? So step 2 is that we look at our rational function, which should now be proper, and we look at the bottom, and we factor the bottom of the fraction as much as we can. So what do we mean by as much as we can? That means that every polynomial, so in particular the bottom that we're trying to factor, we have to write it as a product of linear factors. So things that look like ax plus b, so 2x plus 1, x plus 5, it's just constant times x plus some other constant, so a product of linear factors, and irreducible quadratic factors, ax squared plus bx plus c, where b squared minus 4ac is less than 0. So what do I mean by these? So quadratic factors are just quadratic polynomials. But in particular, we're interested in irreducible quadratic polynomials, which are ones that cannot be factored anymore. So these look like ax squared plus bx plus c, where b squared minus 4ac is less than 0. So it's very important that when you do this factorization as much as possible, you check that any quadratics you have left over, they should be irreducible. If they're not irreducible, then you have to go one step further and write them in terms of linear factors. So we want to have only these two types of things. Okay, so for instance, here are some factorizations. If we look at x squared plus x minus 2, that can be factored as x minus 1 times x plus 2. X squared plus 2x plus 1 is equal to x plus 1 squared. So for instance, the first example, there were two linear factors that were different. So there were non-repeated linear factors. On the second one, it was x plus 1 squared. So we sometimes think of that as a repeated linear factor. The x plus 1 is repeated. X plus 1 times x plus 1 is x plus 1 squared. Okay, then another example, we could look at x cubed plus x. Then you can see straight away you can pull out the x. That's x times x squared plus 1. And now the x squared plus 1 is irreducible. We can't factor it anymore. And if we want to check that's irreducible, let's think what the a and the b and the c are. If we compare it to ax squared plus bx plus c. Okay, here a would be 1, b would be 0, c would be 1. B squared minus 4ac, b was 0. A was 1, C was 1, so that's going to be minus 4, which is less than 0. Okay, so this is acceptable because x squared plus 1 is irreducible. Whereas, for instance, x squared minus 1 would not be acceptable because we can split it as x plus 1, x minus 1. Okay, and then, for example, they could get quite complicated. X to the 4 plus 4x squared plus 3. This could be factored, for example, as x squared plus 1 times x squared plus 3. This will be quite a hard factorization. And as for how to find these factorizations, so sometimes it's just trial and error, which would work pretty well with the first three. Just kind of look at it and see what's happening. But one useful tip, especially with finding linear factors, is that if you plug in a value and the polynomial is 0, then x minus that value is actually a factor. For instance, if we look at the first one, x squared plus x minus 2, if you plug in 1, you get 1 squared plus 1 minus 2, that's 0. So if you plug in 1, you get 0. That means that x minus 1 has to be a factor. Or if you plug in minus 2, we get 4 minus 2 minus 2, we get 0. So x minus minus 2 or x plus 2 has to be a factor. So if you're stuck and you're trying to find factors, you could try to plug in some values. And typically I would pick whole numbers, and whole numbers kind of close to 0 on either side. Otherwise it's going to get way too complicated. But that's one thing you can try if you're having trouble finding the linear factors. Okay, so this was step 2, just to summarize. Step 2, look at the bottom, factor it as much as you can, irreducible quadratic factors and linear factors. Okay, last slide, going on to step 3. Let's suppose we already did step 1, which means that our rational function is proper. And we already did step 2, which means that the bottom q of x is completely factored into these linear terms and irreducible quadratics. Then we have to use that information to write our rational function as in terms of partial fractions that are easier to integrate. And the types of terms we get are going to look like the following. So they're going to look like constant divided by our linear term to some power, or linear term divided by a quadratic to some power. So there are going to be several different cases that we'll talk about separately. Right now it looks kind of confusing, but if we look at q of x and we see some linear factors in q of x, so for instance, in our factorization, we have things that look like ax plus b, then we're probably going to get some terms that look like ax plus b to different powers on the bottom. And if in our factorization of q of x, we see quadratics that are irreducible, that look like ax squared plus bx plus c, then we're going to get some factors of those also, some of those factors also in our partial fractions decomposition. So we'll see there are going to be several cases, and we'll see how to write our rational function in these forms depending on the cases. The cases are going to depend on what q of x looks like when we've done the factorization. Okay, and we're going to discuss each of these separately, and since there are 4 cases, I think it makes sense to break it up. So just to summarize what we talked about, rational functions are things that just look like polynomial divided by some other polynomial. We want to integrate them. To do that, we should write them in a different form, which is called partial fractions form. That's going to make our life way easier. Step 1, we said we should make sure it's proper. So the degree of the top is less than the degree of the bottom. If it's not proper, we have to use algebraic long division to make it proper. Then step 2 is to write the bottom as a product of linear factors and irreducible quadratic factors. And then step 3, we have to divide it into different cases depending on what the factorization of the bottom looks like. And there are going to be 4 cases that we'll talk about in a second. Okay, thanks everyone. See you next time.